Thank you. So I'd like to begin by adding my thanks to the organizers of the conference. I'm very happy to be here over the next few weeks. So today I'm going to be talking about the amplituhedron from a perspective we've been referring to as fibrations of fibrations. This is based off two papers on the left with Livia Ferro, Thomas Wojtkowski, and Jonas Stauknecht. And this stemmed from some earlier work of Jonas and Tomek from the paper on the right. So one of the big advances over the last 10 years has come from the observation that that scattering amplitudes can be encoded as the differential canonical form of some positive geometry. So how this story normally goes is you have your kinematic space on which your scattering amplitude is defined. Within this kinematic space, there's some subregion, which is carved out by some positivity conditions. And this is your positive geometry. And to every positive geometry, you can associate a unique differential canonical form with logarithmic singularities on boundaries of all codimensions. And this canonical form encodes for you scattering amplitudes in the theory you're considering. So in particular, this has seen success in, well, most notably, n equals 4 super Yang-Mills, but also for ABGM theory and trace phi cubed. So I'm going to say that all again, but referring to this picture now, because I'm going to be drawing it again and again. So when I draw this picture, the black space you just think of as the tree level kinematic space. The red region is your positive geometry, your positive subregion, and it's the canonical form of this thing which we want to compute. So we'll be focusing on n equals 4 super Yang-Mills, and we'll be, in particular, would be interested in the positive geometry, which encodes tree-level scattering amplitudes and the all-loop integrand for planar n equals 4 super Yang-Mills. And depending on the description of the kinematic space which you prefer, this kind of positive tree comes with different names. So if your favorite kinematic space is momentum twistor space, we call this positive geometry the amplituhedron. Otherwise, if your favorite kinematic description of kinematic space is spinor helicity space, then the correct positive geometry, well, its name is the momentum amplituhedron. And as I said, these encode tree level scattering amplitudes and the all loop integrand of planar n equals 4. And it's in these two spaces at the top, which the bulk of the work on either the amplituhedron or the momentum amplituhedron have taken place. But there's a third description of tree level kinematic space given by dual momentum space, which will be the focus of the talk today. So we'll be studying the momentum amplituhedron, but in dual momentum space. So an outline of the talk today. I'm going to begin with some just basic kinematics, just to recap. Then I'm going to move on to the definition of the momentum amplituhedron, focusing on its description in dual momentum space. And if you get one thing out of the talk today, I hope it is that you understand what I've written in color. So I hope you understand what I mean when I say tree level chambers, one loop chambers, and the idea of fibrations of fibrations. And I'm going to demonstrate the definitions through some examples at 1 and 2 loops. So the main result of our most recent paper, and I guess the main result of this talk, is that we provide a new formula for the 2-loop MHV integrand inspired by this idea of fibrations of fibrations, which I will explain. So some kinematics. Scattering amplitudes are defined on the space of n massless momenta subject to momentum conservation. And there's a couple of descriptions of this setup, one being spinor helicity space. This can be motivated by wishing to trivialize the massless on-shell condition. So we introduce lambda and lambda tilde variables for each momenta, and these are subject to momentum conservation. And in this formalism, things that show up all the time are the angle and square brackets, which are given by the determinants of your lambda and lambda tilde variables. On the other hand, we can choose to trivialize dual momentum conservation. So we picture lining our momenta up back to back. And instead of talking about the edges of this polygon, we choose to talk about its vertices, the dual momentum variables, the xi. And then the massless on-shell condition is just that consecutive points on this null polygon are null separated. So since we'll be working most of the time in dual momentum space, I just want to recap a couple more definitions, which will be important when we move on to defining the amplituhedron. So we'll be working in 2,2 signature, such that the distance between 2 points, x and y, is given by the top formula there. And in particular, one thing I want you to know is that if you hand me a point x in dual momentum space, I can split R2,2 into 3 parts. Those points which are positively separated from x, those points which are negatively separated from x, and those points which are null separated from x. And in particular, it's this positive one which will be playing an important role when we get to the amplituhedron. The second key fact I wanted to say is the notion of quadruple cuts. So now if you hand me 4 points in dual momentum space, xi, xj, xk, and xl, and you ask for all other points which are null separated from all xi, xj, xk, and xl, this problem will have 2 solutions. Them minus ijkl, refer to them as quadruple cuts. So these things will be playing an important role to come. So moving on to the definition of the momentum amplituhedron. So as I said, the momentum amplituhedron is defined in using the spinor helicity formalism. So the space of all lambda and lambda tilde subject to momentum conservation. So that's our big black space here. As I said, within this region, within this kinematic space, there's some very nice positive region carved out by some positivity conditions, and they're given by, okay, your angle and square brackets being positive, together with sign flip conditions, okay? The precise definition I'm not so interested in. It's just this picture of having some region of the kinematic space defined by some positivity constraints. And if I calculate the canonical form of this red positive region, this will encode for me tree level scattering amplitudes for n equals 4 super Yang-Mills. Sorry, K is just the space of tree level kinematics. So, okay, the helicity sector. So like MHV. It's to do with the sign flip conditions. So these sign flip conditions, you'll say there's some your angle brackets, and you look at 1, 2, 1, 3, 1, 4, 1, 5, and there has to be some certain number of sign flip conditions, and this K is related to this K here, which I can't remember how, but that's how it's related. Yes, yeah. Mm-hmm. Thank you for the question. So we want to describe this in dual momentum space. So if I take a point here in my red region, this will define for me some set of lambda and lambda tilde, which defines my tree level configuration. And I can map this set of lambda and lambda tilde into dual momentum space, where I'll be handed a null polygon with vertices xi. So now when I draw this picture, I want you to think of each point here being defining for you a null polygon in dual momentum space. So since we're in a very nice positive subregion of the kinematic space, these null polygons you get aren't any old null polygon, but they inherit some of the positivity constraints from the definition of the momentum amplituhedron. In particular, each vertex of the null polygon is positively separated from every other vertex. And again, there's some sign flip conditions on distances in dual momentum space, which isn't going to be important to the story. 2, 2. Yeah. The geometry you get define the sign flip conditions are part of the definition of the geometry you get for the amplituhedron or momentum amplituhedron. Yeah, I can't remember the precise thing, but it's like you can, because you can look at the distances between two. So in what you look at is the distances between some of the xi's with some of the quadruple cuts. And this, you can read off the k from the null polygon like this. I don't know how to answer your question. Okay. So yeah, just to recap again, when I draw this picture, every point in the red region we're going to think of as a null polygon in dual momentum space. So that's the situation at tree level. So the data we have in dual momentum space is just some null polygon. But in order to talk about loops and the loop amplituhedron, loops are described in dual momentum space by points. So at one loop, what we have now in dual momentum space is a null polygon together with some additional points, y1. So now if we treat the tree level as fixed, so fix your null polygon, the loop momentum amplituhedron will define for you a positive geometry for the loop variable y1. And if you translate this into dual momentum space, this will define for you a region in R2, 2 in which the y1 variable is constrained to live. Okay, and this region to which Y1 is constrained, I'm going to refer to as the one loop fiber. And the structure of this one loop fiber depends on the null polygon that you've chosen at tree level. And now I want to move on to describing how we define this one loop fiber. So again, as I said, no, I think tree level comes first, and then so we fix our null polygon, and the one loop fiber is defined by those set of points in R2, 2, which are positively separated from each vertex of your null polygon. So the picture we have is we have a point corresponding to a null polygon. We shoot out all null cones. We're in R2, 2, so maybe cones is the wrong word, but that's the one I'm going to use. Shoot out all null cones of the xi. This will split the R2, 2 to a positive and negative part with respect to each xi. And if I take the intersection of all these positive parts, this will define for me some geometry we call the one loop fiber in R2, 2. And it's your Y1 variable, which is constrained to live inside here. Okay, again, there's some sign flip conditions. You can assume with every definition I get that there's some additional sign flip conditions. So a few more words about this one loop fiber. So its codimension 1 boundaries are given by the conditions of Y1 being null separated from one of the vertices of your null polygon. And the vertices, this is an important point, the set of vertices of this geometry are given by your xi variables together with some set of quadruple cut points. So it brings me to the first keyword I wanted to get across. So now what you can imagine is varying your tree level configuration, computing this one loop fiber, and looking at how its combinatorial structure changes as you vary the level configuration around. And in fact, it does change. And the key idea is to split the tree level kinematic space into regions for which the combinatorial structure of the one loop fiber remains constant. And these subregions of the tree level kinematic space in which this holds, I'm going to refer to as tree level chambers. And maybe a picture will help. So again, red is tree level momentum amplituhedron region. Now this is split up into, well, in this picture, 3 tree level chambers. If I take a null polygon in this chamber, compute its one loop fiber, I will get something, has some set of vertices. If I take another point in the same chamber, I'll get the same structure. Now, if I go far enough and cross a boundary from one chamber to another and compute the one loop fiber, I'm going to get a different combinatorial structure. And right, it is, so when you go from one chamber to another, it's like some set of quadruple cuts appear as vertices of your geometry, and in the next chamber you have a different set. So I guess it's No. Well, I mean, the important information when we go to compute canonical forms will be the set of vertices. What I'm about to describe is that from when you know the set of vertices, you can almost immediately write down the canonical form for the loop fiber. So yeah, what's the upshot of this at the level of canonical forms then? Well, simply at tree level, it gives us a new. I don't know much about the lower dimensional. Okay. So simply at tree level, it gives us a new way of writing the canonical form for the tree level amplituhedron as a sum over chambers, as a sum over the canonical forms for the tree level chambers. More importantly, at one loop, so since the combinatorial structure within a chamber is constant, so too is the expression for its canonical form. So this leads to this kind of factorized form for the one loop integrand, where we have a sum over tree level chambers. We have the canonical form for the tree level chamber, wedged with the canonical form of the one loop fiber. And it's this. So when I say one loop integrand is a fibration over tree level, it's kind of this form of the writing the one loop integrand to which I'm referring to. So, okay, I haven't actually told you how to compute any of these things, but today I'm just going to talk about this guy, the canonical form for the one loop fiber. So in order to do so, it's useful to take a step back and think about canonical forms of simple polytopes. So when you have a simple polytope, one way of computing its canonical form is via a sum over vertices. So here we have a pentagon with faces f1 through f5, and on the right, I've written the canonical form. This has 5 contributions. If we zoom in to look at the first one, we see it takes the form d log f1, wedge d log f2. f1 and f2 are facets of your geometry, and they come together to meet a vertex. So we see this contribution coming from this vertex. And we want to use the same philosophy when computing the canonical forms for the one loop fiber. So now here's a simple recipe for computing the canonical forms for the one loop fibers. Well, all you have to do is determine the set of quadruple cut points which appear as vertices of your geometry. And when you've done this, you have to figure out the correct contribution from a given vertex, and it takes this form. So you have 2 terms, one which is completely analogous to the slide before. We have d log of the 4 facets which meet at that vertex, and another contribution which looks like a box integrand. Again, these details aren't important. I just want to emphasize this picture of, in order to compute the canonical forms for the one loop fiber, all we need to know is the set of its quadruple cut vertices. So let's take a look at an example. So example is for MHV at any n. It turns out the tree level space consists of a single tree level chamber. So the canonical form of the tree level chamber is just equal to the entire amplitude. Now I can take a null polygon in this chamber, compute its one loop fiber, and look at its set of vertices. And it turns out the set of vertices take the form Q plus II plus 1, JJ plus 1, which brings us to the formula for the one loop integrand. We have the tree level chamber, which is just the entire tree level, and the canonical form for the one loop fiber as a sum over all its vertices. That example was somewhat trivial because as a single tree level chamber, the first example when this is no longer the case is NMHV6. So for those of you familiar with the NMHV6 tree level amplitude, you know it can be written in two different ways, either as a sum over odd Rn variants, R1 plus R3 plus R5, or as a sum over odd even Rn variants, R2 plus R4 plus R6. And this is what you would get from, for instance, BCFW. But we're not interested in the BCFW decomposition. We're interested in the chamber decomposition. And it turns out, in this case, a tree level chamber is defined by the intersection of one even Rn variant and one odd Rn variant, in which case we find 9 tree level chambers. So at one loop, now all we have to do is take a null polygon in each chamber and look at the set of vertices for each of the one loop fibers. So I just do this for one example then. So we take a null polygon from the chamber defined by Rn variants R1 and R2, and we find the one loop fiber contains 8 vertices corresponding to the 8 contributions in blue. And the plus ... are the remaining 8 chambers. That's everything I wanted to say about the one loop case. But if you're interested in some of the details for higher N and K, you can refer to this paper from last year. What I wanted to get to is 2 loops. So now the data we have in R2, 2, as before, is our null polygon, loop momentum point Y1, and additional loop momentum point Y2. So now imagine fixing our tree level data and fixing Y1 to be some point in the one loop fiber. Okay, then the 2 loop amplituhedron will define some positive geometry for the second loop variable Y2. I translate this into R2, 2. This will give me some region in which Y2 can live. Now this will depend on X, but it will also depend on Y1. So just to recap, because I keep saying words that you've never heard before, we have our null polygon, the one loop fiber in which Y1 lives, and the 2 loop fiber in which Y2 lives. And I want to define this 2 loop fiber for you now. So in fact, it's a subset of the one loop fiber constrained with the additional constraint that Y2 must be positively separated from Y1. And those familiar with the original definition of the amplituhedron, this corresponds to your mutual positivity condition between loop momenta. So now we do the same as before. So let's fix tree level now. This defines for us a one loop fiber in which Y1 lives. And as I scan Y1 around the one loop fiber, I compute the geometry for the 2 loop fiber. And generally, as I move it around, its combinatorial structure is going to change. So again, the key idea is to split the one loop fiber now into regions such that the combinatorial structure for the 2 loop fiber is constant. And I'll be referring to these as one loop chambers. So you can see it's just completely analogous to the situation at tree level, but I've just gone up by one loop. A picture. Again, we have tree level. Take a null polygon. We get a one loop fiber. Now, this one loop fiber is itself split into one loop chambers. Take a point y1 in one of the one loop chambers, calculate the geometry for the two loop fiber. I'll get something. If I take a different point y1 within the one loop fiber, I'm going to get a different geometry for the two loop fiber drawn in pink. So I guess just to emphasize now, the two loop fibers and their corresponding one loop chambers have two indices. The first indice locates where you are in the tree level chamber structure. The second index locates where you are in the one loop chamber structure. So at the level of canonical forms, we have a similar situation as before. So we have a sum over tree level chambers, an additional sum over one loop chambers, canonical form for the tree level chamber, canonical form for the one loop chamber, and finally the canonical form of the two loop fiber. And you just choose. You can, yeah. It's just, it is, yeah, it's what you can do. Yeah, you're making a choice of which one to prioritize in your loop kind of tower. Sorry? It means, okay, I don't actually know what the definition of a fiber bundle is, but I mean, it's just a catchy title. Yeah, well, fibrations of fibrations, whenever I say it, all I really mean is writing the one loop integrand, sorry, the two loop integrand, or whatever loop, in this kind of way which emphasizes this chamber structure. Yeah, I thought about this. I don't. It'd be. I think it's an interesting question. But I don't know. Yeah.
If you make one choice and then the other choice and write two different formulas, are they immediately manifestly equal on the nose, or is it non-trivial?
I think it's quite non-trivial.
Summing over choosing one and then the other, plus choosing this one for the, you're just making one choice, but the result has to come out of the metric.
Oh, I see. Yeah. Yeah. Okay, I don't want to say that because I'll lose time, but maybe at the end. Okay. Okay, and this is the formula which I refer to as a fibration of fibration. The last thing I want to tell you about is how to characterize the set of one loop chambers for MHV integrands. So, as I said, at tree level, sorry, I'm going to do this for an example at 5 points. As I said, at tree level, there's a single tree level chamber, so there's a single one loop fiber. It has some set of vertices given by the xi, together with some set of quadruple cuts, given by q plus 1, 2, 3, 4, together with its cyclic copies. By definition, all points Y1 within the one loop fiber are positively separated from each of your xi. This is not generally the case for the quadruple cuts. So now if I scan Y1 around the one loop fiber and look at the sign of all the distances from Y1 to each of the vertices of the geometry, this is going to give me a different sign pattern for each of these distances. And the different sign patterns which you get for these distances exactly characterize the set of one loop chambers. So for instance, at 5 points, we find 11 chambers. 5, where we have 2 points positively separated from Y1. 5, where we have a single point positively separated from Y1. And a final guy where no one is positively separated from Y1. Won't have time to go over this picture, but you can encode this information by kind of well, not a triangulation, a decomposition of the pentagon by introducing all chords of the pentagon. Just to note, a warning: you can't do this for higher points. And this allows us to write the two-loop integrand as the fibration of fibration, because we now know the chamber structure. And I'm not gonna, okay, maybe one thing for those of you in the know, the canonical forms of the two-loop fibers can have a very simple expression in terms of box integrands and chiral pentagons. Not important. So the last thing I want to do is just summarize results of our recent paper from a couple of months ago. So we were able to determine the full set of one loop chambers for all MHVN by determining all possible sign patterns for these distances to the vertices of the one loop fiber. And it turns out they're counted by the Eulerian numbers. And this is closely related to the work of this paper, where chambers of the M equals 2 amplituhedron were considered. We got simple expressions for the canonical forms of all two-loop fibers as a sum over chiral pentagons and chiral boxes. And finally, we had a new formula for two-loop MHV integrand for all n, inspired by this fibrations of fibrations idea. So to conclude, I hope you understand what tree-level chamber is, a one-loop chamber is, and the title of my talk. And if you don't, you'll have another opportunity next week, because Jonah's going to be talking about similar things, but for ABGM theory. So future direction include higher K at 2 loops, higher loops at low K, and other theories such as ABGM. Thank you very much for listening. Oh, Eulerian numbers. Can I describe? I don't think I can describe in a very so like it's the key thing is that what helped us find this is the results from Lauren Williams and other people in this paper. They describe chambers of the M equals 2 amplituhedron for some K, which I can't remember, some low K. And they found that the chambers there were counted by the Eulerian numbers, and this is related, and they mapped the chambers of the M equals 2 amplituhedron to simplices in the hypersimplex. Yeah. And it turns out we can kind of have a one-to-one mapping between our chambers and theirs. If you're familiar with the hypersimplex and that. Well, for NMHV, we can actually work. I'm probably not answering your question, but for NMHV, we can compute the full set of tree-level chambers. Or for instance, since R1 plus R1, 3, and R5 appear in one triangulation of the tree level, they both can't appear in a chamber because they don't overlap. But sorry. To some extent, I guess, but I don't think of it as a residue theorem or anything.
Okay, now that's the last question. On your last slide.
Yes.
Okay, what about 4-point? 4-point integral, completely
Yeah.
Is it simple enough that you the hybrid order for 4 points?
Oh, sorry. Okay, that's 4 points. Yeah.
Oh,
That,
chamber.
yeah, that's 4 points. Yeah.
All right, thank you.
Thank you.